Hi, I'm Patrick Madden from SUNY Binghamton. What I'd like to present in this paper is kernel mapping techniques for deep learning neural network accelerators, and it's joint work with some of my students. Sarp Ozdemir is an undergraduate, and he's graduating this semester. Mohammad Khasawneh is a PhD student, and Smriti got her master's degree about a year ago. The focus is on machine learning accelerators, and in particular mapping compute kernels onto compute fabric. This is motivated by the ISPD 2020 kernel mapping contest. To get a little more detail on what we're doing, there are deep learning kernel graphs, basically a series of convolution operators, aggregation, min-max, thresholding, and deep learning applications are built from connecting tens or hundreds of these layers of kernels together. There are a number of different styles. I've got a VGG style shown on the left and a resonant style shown on the right. Tensors pass through this, and so there's a lot of computation that happens in each layer of the deep learning kernel graph. We're really motivated by the Cerebras CS1, which is a wafer scale deep learning accelerator. It's got a grid of about 633 by 633 processor cores, so it's a very, very large chip with a lot of cores. And if we want to maximize the performance of a deep learning kernel graph, we have to minimize the maximum delay of any compute kernel in that graph. Data is going to pass through in a pipeline fashion, and so it's going to be the slowest link that's going to be the constraining factor. The kernels are compiled, and they're going to be assigned to rectangular grids of compute cores. And there are opportunities to unroll parallelism. If you unroll and use more cores, you obviously get better performance, but you're also using up more resource. And so there's a trade-off of how much you can unroll a particular kernel and what it takes from other kernels in that graph. Each of these compute cores has a fixed amount of local memory, and so there's a constraint with this as well. When we unroll the parallelism of a compute kernel, we've got to watch the height and width, the delta t, the time that it takes, and also the memory. Any given kernel in a kernel graph might have a number of different implementations that would be legal and feasible, and we'll call each one of these a variant. There are usually a large number of possible variants for every single kernel. And to make this problem a little bit more concrete, what we've got here is a figure from Cerebras. This is a CS1 processor, wafer scale processor, and they've got a kernel graph mapped to it, so you can see the rectangles highlighted. And each one of these is a compute core or a compute kernel doing some number of processing with lots of compute cores within it. The dashed light yellow lines are the connections between the kernels. And so we have a lot of rectangles, some connections between, and in some ways this is going to look a lot like a floor planning block packing problem, but there are a couple things that are a little bit unusual here that we can exploit and make for a better solution. Packing rectangles is always difficult, but we're going to use the nature of the kernel graph to our advantage. And what I want to really highlight here, and this is important, is Rent's rule. The connections that you'll see in a kernel graph don't really look like what you'd find in a normal VLSI circuit. In typical circuits, Rent's rule is tracking the number of pins on a subcomponent versus the number of blocks within that. And you normally have a Rent parameter in VLSI design of 0.6, 0.7, 0.8. If you have a regular mesh, the Rent parameter R is going to be 0.5. And what we're finding with these kernel graphs is really effectively a Rent parameter of 0. It's almost always a sort of single input, single output chain of compute kernels, or if there's fan out, it reconverges almost immediately. So for the ISPD contest, there are a couple of metrics that we tracked. The delta t, that's the maximum delay of any kernel. It's basically how fast the pipeline can run. And also the distance between the centers of the kernels. It's also important, but weighted differently. And there was some charge for adapters for differences in how loops are enrolled. We're omitting it from this work. The low Rent parameter was something that was noticed by a number of teams that were competing in the ISPD contest, and in particular the winner of the ISPD contest, which was CU Poker from CUHK. They observed this and took advantage as well. What you can do is you order the kernels by just a topological traversal. This gets you a good ordering, and then what the CU Poker team did was they selected a delta t, a target speed, and they were doing this through binary search, trying to find the fastest delta t where you can find a feasible solution. For each delta t, they tried to implement using only a single horizontal row. So each kernel was unrolled to the maximum height of the chip, and then as narrow as possible, and tried to pack everything into a single row. If this worked, they had a solution, and many of the contest benchmarks fell into this category. Sometimes, though, second row was required, and this is where they ran into a bit of a computational complexity problem. One row, h1 tall, everything's good, but if you have to split it into h1 tall and then the remainder of the space minus that, you have a whole lot of combinations to explore. If you need to go to three rows, it becomes even more computationally expensive. And I want to note something about the cost function for the ISPD contest that resulted in what I consider a little bit of unusual layouts. What I've got here on the right-hand side is two implementations where there are 16 compute kernels. On the left of those two, every kernel is implemented in a square arrangement, and this might look something like you might see in a normal VLSI chip. You want to avoid high aspect ratios because the internal wiring would be prohibitive. On the right is the solution that would be heavily favored by the ISPD contest benchmarks, or contest objectives. Still 16 kernels, but spanning the entire height of the chip and extremely narrow. The wire length differential between these, as computed by the ISPD contest, the one on the left would be about a factor of 5 worse. To dive into our approach and how we approach this problem, like CU Poker, we first did a traversal of the graph topologically. So we find the ordering, and then we go and implement and find every possible variant for the compute kernels. We can do this through brute force, and there are many, many thousands. So if I've got this compute kernel K1 shown in yellow, I might have 3, that's what I'm showing in this figure, but it might be hundreds or thousands. We can weed this out and reduce the solution space by using Pareto optimization, looking for non-dominated kernel implementations. We're using Bentley's efficient divide and conquer Pareto algorithm, and so that's done fairly quickly. Following that, there's a little bit of dynamic programming. We first find horizontal strips, and then we stack those strips into stacks. I'll talk about that a little bit more in just a minute. First, I want to talk a little bit about kernel variants. Again, CU Poker was using a numeric method. They picked a target, t, delta t, and then found the maximum height and minimum width they could find. What we do is we find a brute force method, and so we simply step through all possible variants, unrolling in different ways, and then filter through with the Bentley's divide and conquer to get non-dominated cubes. And these non-dominated, if something has a smaller width or smaller height at the same time, it's dominated. We can find these variants very, very quickly. And there's a neat thing that comes out of checking through every possible variant. We can establish a performance bound on the entire kernel graph. So for any time delta t, any particular speed, we can find the smallest kernel implementation that meets that target threshold. So for the entire graph, we can find the minimum number of cores that are needed to hit that delta t target. That gives us a lower bound on the possible performance. We know how fast this thing could possibly run. And we can also get a curve that shows how fast this is theoretically possible based on the different number of cores. And that's what's shown on the right. Knowing what we know about the target speed, we can then select a target delta t, similar to what CU Poker did. And our approach is through dynamic programming to find the actual layout. We're going to first do horizontal strips, and let me briefly explain what's happening here. If I've got two kernels, kernel I and kernel I plus 1, they're going to go together in series, and I can take every variant of kernel I and every variant of kernel I plus 1, combine them together, and that gives me the pair of them, and then I can find non-dominated set out of those pairs. Again, using Bentley's dynamic programming or divide and conquer approach. And I can build up longer and longer strips. So I do I and I plus 1, then the pair of I and I plus 1, and I plus 2. And it's just classic dynamic programming to build horizontal strips. Once we've got those strips, we can then do stacks of them. So I might want to find the solution for packing all k1 to kn. I can pick some value kj in between and split it into 2 chunks and stack those on top of each other. The recursive dynamic programming approach should look very similar to matrix chain multiplication. While we're doing this, it's always possible to prune the solution space and make things run a little bit faster. First, we can eliminate any kernel variant that exceeds the target speed, so we can discard all those. We also know how many compute cores we have available, and so we have a number of ways we can detect that we're going to overflow the area bounds and discard those solutions. In particular, when we combine a pair of kernels together, there may be some wasted space because their heights or their widths might not match exactly. And so we know we're losing a little bit of space when we combine them. And if the wasted space exceeds the slack we have available for the design, we know that we can prune that solution too. So let me dive into results for a minute. Again, the ISPD contest objective function was to minimize the delta t and also interconnect length. CU Poker was definitely the winner. They did very well. Our approach finds the smallest delta t for all but 2 benchmarks, but we lose on the interconnect length metric. And because we know what the optimal bound is, we're able to detect within a few percentage points of the optimal delta t on nearly everything. And we can get almost complete utilization of all compute resources on the CS1, so we're not wasting very much space. The packing that we're doing with horizontal strips and just lining up is not costing us anything in the utilization. We don't pay a penalty for this. If the scoring function took into account the kernel aspect ratios, I think our approach would fare much better. Roughly square kernel layouts with more rows may be better in practice. And I want to thank the folks at the CU Poker, particularly Professor Evangeline Young and student Benchen Yang, who were extremely helpful. We had a bug in our implementation and they helped us fix it after the contest. So let me show the results here. A lot of numbers on this table, but the important ones to look at are on the lower right-hand side. Delta t relative to CU Poker is 0.781. So we were consistently finding faster, lower delay implementations. The wire length, however, substantially higher, about 2.39, so substantially higher wire length cost. And the scoring, we're about 1.5 relative to CU Poker. Again, it comes into how we weight the objective functions and balance things out. Note the utilization, next column, 0.888 on average, so about 88%. And for many of some of these designs, it's close to 98, 97%. So we're getting very close to total utilization. When the utilization is lower, it's usually because we've unrolled all the available parallelism and there's not any more that of the resource can be used. And the bound relative to the optimal, we're running about 1.04, so about 4% higher than the optimal delta t that could be possibly achieved. Now I want to talk a little bit more about a couple more things. One thing we noticed, and again, this comes back to the rent parameter observation, we don't have the same sort of pressure to put everything onto the same single die that you might have with a conventional VLSI circuit. We're flowing a tensor into the CS1, and we could certainly split the kernel graph onto a second processor, and if we can match the input in, the bandwidth coming in, to the bandwidth going out, we could chain 1, 2, multiples of them together. Again, this is something we could not do or wouldn't be reasonable to do with a conventional VLSI circuit with connections going in every direction. But because of the structure of the kernel graph, this is something that's actually feasible. And we performed a few experiments with this. Not all of the benchmarks were large enough to be able to be streamed across multiple CS1s, but what we did here is for some of these benchmarks, where they had an opportunity for additional parallelism, we did experiments to find out what would happen if we mapped it onto 4 CS1 processors. The delta T goes down because we're able to split the work across multiple processors, and we get a speed up. On average, with 4 of the CS1s, we'd expect a speed up in the delta T of about 3.61, so close to linear. And here's a figure that shows the multi-chip or the multi-CS1 mapping. On the left, we've got all the kernels from one of the kernel graph benchmarks mapped onto one CS1. And we can take the same sequence and then split it across 4 different CS1s. That's what's shown on the right. And we're doing this, one thought is to really focus on more sustainable deep learning architectures and acceleration. Typically, a new chip comes out and the old ones become obsolete fairly quickly. Because of the nature of the kernel graphs, if we simply provide enough bandwidth in and bandwidth out, we map the kernels across multiple accelerators and be able to extend the useful lifetime of an accelerator and be able to add on to an existing system by simply chaining a new processor on. And this hopefully gives longer life and lets older technology be combined and used effectively with newer technology. Thank you very much for your time. I'd be happy for questions.